So now it's my great pleasure to introduce Antonina Kolokolova. Antonina is one of those theorists who is interested in many different things, not only proof complexity, but also in the practical side of solvers, for example. So I've had the pleasure of working with her on many papers together, and she's also interested in the connections between theory and neuroscience. She's well known for her work in proof complexity, and she did her PhD under the supervision of Stephen Cook, and is currently a professor at Memorial University of Newfoundland. So without further ado, Antonina, please go ahead.
Thank you so much for the nice introduction, Vijay. Okay, so thank you so much, Albert and Benedict, for spectacular talks. It was so cool to listen to you. Okay, so what I'm going to talk about is one more line of connections, kind of in the opposite direction from what Benedict talked about, not from proof complexity into finite model theory, well, with proving things and going back, but how we could take results in descriptive complexity and actually build reasoning systems on top of them. So basically, we have kind of three realms in which we talk about problems. One of them is the search problems. For example, how hard it is to find a path in a graph. Another one, the one that you just heard a lot about, is expressive power. What does it take to say that the graph is connected? But the third side, the one that shows up more in proof systems, what does it take to prove properties? For example, that reachability is transitive. And loosely speaking, those three realms would be your classical algorithm complexity theory, descriptive complexity and finite model theory, and for the provability, proof systems, as well as its uniform counterpart, bounded arithmetic. And you've seen a lot about the relation between complexity and the finite model theory today, descriptive complexity. You've seen some of translation from proof systems into descriptive complexity in Benedict's talk. And actually next week, in this workshop, next Wednesday, we are going to have a session on kind of mathematical foundations of SAT, with talks going more into arithmetic and probability and that side of things. So what I want to talk about today is how results proven in descriptive complexity setting can let us build something in. Let us build reasoning systems. So it's this direction. So just one caveat that here I'm just going to talk about the uniform classes and uniform system. There was a really nice question about non-uniform side of finite model theory, but what I want to focus on today is the actually uniform side of finite model theory, because to me, in a way, some of those characterizations that Albert talked about are uniform counterparts to what we think about as the propositional satisfiability problem and friends. And in fact, Pagan theorem is kind of a counterpart of Hooke's theorem, where rather than getting a class of formulas, you just get one formal uniform setting. So, and another thing where we need uniformity, we will be talking about uniform classes, even for very small classes. So we could talk about the class uniform Dirac time uniform AC0, which has a very direct connection with first order logic. So more precisely, and I will define those things, what I want to show today is how you could start with logics, in particular fragments of second order logic with nice descriptive complexity characterization, and use them to build theories with the same power, and show what exactly you need to get theories of the same power from those characterizations. So you just heard Albert's talk, and he was talking about the groundbreaking result in '74 of Ron Pagan, who shown that NP corresponds precisely to existential second order. And the proof is again a variant of Hooke's theorem, except rather than generating a different formula for different input and run of the Turing machine, you actually have just one formula defining the tableau of the computation. And this allows you to be in a setting where you could actually talk about one formula specifying a problem as opposed to a family of problems. So for example, in proof complexity, we often talk about pigeonhole principle as a family, but here pigeonhole principle is just a single formula. Okay, so Pagan's characterization shows that without any assumptions on the underlying structure, NP corresponds to existential second order formulas. In 91, Eric Gradle extended it to show that subclasses of second order logic, in particular second order logic where the formulas are of this form, also correspond to well-defined complexity classes on structures containing successors. So in particular, if you take existential second order formula of this form and you restrict the formula to be a Horn formula, where I guess the Horn with respect to those P1 to Pk predicates, then on successor structure, this logic captures exactly polynomial time. And when you restrict the formula to be 2CNF, you could capture non-deterministic log space. And actually, he had characterization for symmetric log space, for log space. It's really beautiful piece of work.
Can you define what you meant by Horn over the predicates?
So I just mean that it's a CNF formula where every clause has at most one positive occurrence of a predicate.
Okay, got it.
So you only consider those as occurrences of the predicate as your variable, so to say, and then it's Horn with respect to that. So another result by Barrington, Immerman, and Strobin, I think there might have been some earlier results by Immerman, but Barrington, Immerman, Strobin gives a Dirac time uniform characterization, shows that if you don't have second order quantifiers, then you just have first order logic with free second order variables, then you capture exactly the class AC0, the class of bounded depth circuits, which is probably the smallest complexity class that you hear people talking about. And the beauty of those characterizations is that the correspondence is exact. If you prove the two logics are equivalent, the corresponding classes are, and vice versa, So as Albert was showing, there are lots of techniques that can be applied in this setting to prove something about logic and then transfer it, well, to proof systems and so on. So in proof complexity, we tend to be more interested in proving tautology, so proving some statement, rather than expressing statements. And a natural question is, if you are operating with a class of formulas with precisely defined complexity, can you say something about the complexity of reasoning with those formulas? And actually, to me, it goes way back to the time when I was undergraduate, and I came to Toni Pitassi asking to do some research with her, and she gave me 2 papers. One of them was Ron Fagan's finite model theory of personal perspective, and another one was Sam Bass's notes on bounded arithmetic. So I read them, got very excited, came to Toni and said, Toni, so how are those related? How do you go from one to the other? There must be a connection. Well, I'm still stuck thinking about the connection many, many years after. So let me just mention very few things about the history of the arithmetic side of it. And next week, we are going to have several talks that will cover this much better and in much more detail by Sasha Radborov, Pavel Pudlak, and Shai Ben David. So I won't spend too much time on it. But basically, piano arithmetic is probably one theory that people think about when they think about power of reasoning in systems, unless you do reverse mathematics or something like that. Piano arithmetic is one of the default theories that we reason about. And later on, people have defined, but piano arithmetic is very strong. It talks about things from computability realm rather than complexity realm. In order to move things to closer to the efficiency question, Parikh defined the bounded version of piano arithmetic I delta 0, but this time it ended up being theory that's a little bit too weak. You just talk about linear time hierarchy and you can't quite go beyond it. Then Steve Cook have defined the theory PV originally as an equational theory, which was designed to capture polynomial time. Exactly. He used Cobham's characterization of polynomial time, recursive characterization, to just define polynomial time functions and operations with them. This theory was later extended, I think, by Krajicek to make to add a bit more Boolean stuff. And probably one of the main defining works in this area is Sam Bass's beautiful thesis called Bounded Arithmetic, where he defined he defined a lot of different theories corresponding to various complexity classes and proved very interesting witnessing theorem, that is, proved that when you can prove something in a theory, then you know the complex. If you prove an existential statement in the theory with certain form, then finding a witness can be done by an algorithm of specific complexity, and the algorithm kind of falls out of the proof. So in bounded arithmetic, just to say what makes it bounded is that we're thinking of all values that are quantified as bounded by the terms in the free variables. And here, when I'm talking about the power of a theory of arithmetic, especially in the correspondence with complexity classes, it's basically what kind of functions can be provably defined in the system by, can be defined in this system. So the system proves there exists unique value of the function. And just one caveat that it can very well happen that there are theories that capture the same class of functions, that is, they prove totality of the same class of functions, and yet one system seems to be more powerful than another system. As in, it's not believed to be that every theorem that one system proves can be proved in the other. So relating this back to propositional proof systems, there is actually a very direct connection, because for those kinds of theories, for one direction, you could do direct translation in propositional proof systems by taking theorems of the theory, converting them into a family of tautologies, and showing that the corresponding proof system can prove that family of tautology. And for the other direction, you could show that the bounded arithmetic theory can prove essentially soundness, more precisely reflection principle, for the corresponding proof system. So even though bounded arithmetic is a kind of a uniform setting and proof systems are non-uniform, there is this very tight connection between the two. And just to mention a few, the theory that captures AC0 would give a translation directly into AC0 Frege, bounded depth Frege. Similarly, a theory for NC1 will give you Frege. And theories for polynomial time, they translate in this way to extended Frege. Okay, so let's now connect the descriptive complexity side and bounded arithmetic side by showing how you could build a theory of arithmetic. And if you have never seen a theory of arithmetic or built one, hopefully this would be a kind of a gentle introduction to one way of doing it. So what we need in the theory, we need a language and we need axioms. And here we are going to take a slightly different path from what Sambas did in his thesis and use a two-sorted theory, which will have a much better correspondence to the descriptive complexity characterization. What I mean by two-sorted is that you have two kinds of objects. You have numbers and you have strings. Just like in descriptive complexity characterization, you have your graphs, predicates as being the second order objects, so to say, floating around. Here you will have strings corresponding to the structures. And the axioms of this theory would be fairly standard. First of all, for numbers, we'll just take the very classic axioms defining how plus and times operate. And here we just need plus and times. For example, axioms saying that for any x, x plus 1 is not equal to 0, and stuff like that. 1 is greater than 0, and so on. Then for strings, we will have very few things. Again, we want to look at them as predicates, so we will just say, we will just use an operator telling us what the bit of a string is. And we also define what the length of the string is, because we want to kind of bound things. So we want to say, can you hear me?
I can hear you clearly, Antonina. Is there anybody else who wants to just say that whether they can hear?
I can hear
Moshe?
you.
Okay, thank you.
Very nice.
I can
So
hear.
I guess Thomas is having some problems there.
And maybe it's, yeah. Okay. Okay, so in addition to those basic axioms saying what you could do with strings and what you could do with numbers, well, add and multiply numbers and take a length of the string and look up a bit. There is one more axiom, and this will be the main axiom that will let us define all sorts of different theories. And basically what this axiom is saying is that if you have a formula from some limited class of formulas, then you could get a characteristic string of that formula. That's really the only thing that we need to build the theory. And now we could reason with those axioms, and in order to do reasoning, in order to do proofs, you could take your favorite way of doing proof. I think Gensen's calculus LK is the most standard underlying way of doing proof, but there is really
So can I ask you a quick question?
please.
X of y, what does that notation mean? Is X a string here and y is a
Yes.
number?
Yeah, it just the y's bit of x when x is treated as string.
Okay. So you're saying if I take the yth bit of X, then it implies Y must be strictly less than.
You kind of interpret one as a true and zero as a false. So another way of thinking about it is x is a set and x of y is whether y is in the set x.
I see. Okay. And comprehension, you're saying there exists a string X. X is a string variable.
Mm-hmm.
I'm trying to, is less than or equal to n. So I guess the bit strings here are being interpreted as numbers implicitly.
Well, the strings are strings. Numbers are mainly used to talk about lengths and indices.
Yeah, but what do you mean there exists an X less than or equal to n? What does that mean?
Sorry, I didn't define this notation. So thank you so much. So what I mean is length of x less than or equal to n.
Okay, so there exists an X such that length of X is less than or equal to n for all integer variables or natural numbers z less than n. So now if z is in the set X, I see. Okay. All right. Got it. But here phi is a formula in this language, or is it a formula over arithmetic?
It's a formula in whatever restricted class of formulas we define, and the power of the theory will correspond to the power of that class of formulas.
Okay.
Yes, thank you. More questions, comments?
Nope, please go ahead.
So one thing that you might be wondering is where is induction, because in piano arithmetic and pretty much all the other theories that I've seen, or vast majority of them, you have an induction axiom. In fact, you could actually, for all the theories that we care about, prove induction, but just to have it to make life easier, here it is. Given a string, you could do induction on the length of the string. So if something, if x of 0, well, if element 0 is in the set x, if you want to think about it as sets, and for every y, if y is in the set x, then y plus 1 is, then n is in the set x. Here's your induction on the length of the string. So this is really all you need to build the theory, and you don't even need induction. And now with those theories, you could prove theorems, you could define functions and prove totalities of the functions, you can convert them to proof systems, and so on. So what kind of theories do we get when we do it for different? So what defines the power of the theory is really what class of formulas we are allowed, the theory is allowed to talk about. So first of all, if we take as a class of formulas existential second order, and here I'm treating the second order objects in the descriptive complexity setting just as strings in bounded arithmetic setting, but this really doesn't matter the translation. The translation is pretty direct. So if you take existential second order, you get the logic for NP predicates. And if you make a theory out of existential second order, you make a theory that can talk about well, things definable by NP predicates. And in particular, you directly get two sorted analogs of Sam-Bass's hierarchy S2. But here's the interesting thing. Sam-Bass proved a beautiful theorem about the theory that operates with SO exist predicates. And the theorem says that if within the theory, you could prove that, well, the function is definable, the predicate is in NP intersect co-NP. So there is a SO exist and a SO for all formulas, and they equivalently define the predicate. Then, in fact, you get that the predicate, the function, is in polynomial time. It's really, really beautiful result and kind of surprising. It basically says that if you reason with NP predicates, and if you can prove that something is an NP intersect co-NP, then in fact it must be in polynomial time. So sort of in the bounded arithmetic world, at least here, the provable NP intersect co-NP is polynomial time. A really cool, really surprising result. And this naturally generalizes to levels of polynomial time hierarchy. You could talk about exist for all exist second order, and it will give you a third level. And again, you could use a witnessing theorem, Bass witnessing theorem, to capture the corresponding deterministic class. But you may ask okay, with NP predicates, we didn't quite capture NP. What we really captured is polynomial time in the case when the theory could prove that something is in NP intersect co-NP. But can we actually take a logic corresponding to a complexity class and get a theory for exactly the same complexity class? What would it take? So before I go that, just to quickly mention for people who are familiar with some Bass's theories, the difference here is that in our language we only have plus and times, but we do have strings. So some already had theories with second order object. He defined theories for P space, for exponential time, and so on. And there he used that extra function in the language in order to define bigger things. But Razborov and Takeuchi have shown that you can go back and forth between the theories with one more extra sort and having this smash operator in the language. So in our setting, we don't have any extra operators, and we just have the string sort, and we get that this is equivalent to S2. Okay, so just to reiterate, how do we get a theory? We take axioms defined in basic arithmetic and add an axiom that says all objects definable in a certain logic exist. So what can we do with it? We could actually extend, if I well, the series Si2 and Ti2 that Sambas defined, there you do allow multiplication on big numbers, small numbers, so you generally have multiplication. But in the setting here, in the two-sorted setting, since you don't have multiplication of the larger second-order object, you could actually get a theory for AC0, where you cannot do multiplication of your objects. And starting from the theory for AC0, you could get theories for all sorts of classes within polynomial time. And how do you get a theory for AC0? Well, remember that Barrington, Immermann, and Strobing told us that first order logic, if you have arithmetic in your language, and well, you have arithmetic in your language in arithmetic, captures the log time uniform AC0. So just define our class of formulas to be formulas with no second order quantifiers. And using beautiful characterization by Eric Gradle, we get a theory for non-deterministic log space and the theory for polynomial time from second order existential 2CNF formulas and second order existential Horn formulas, respectively. But this correspondence is not exactly automatic, because remember, if we had NP formulas, we didn't really quite get NP. We got polynomial time, and this is really non-trivial result. When do we actually capture precisely the theory? And this depends on how hard it is to prove closure properties of the complexity class. So what do I mean by closure properties? We would like to work with really nice complexity classes. And nice complexity class, of which NP is not quite, are closed under first order operations. You could take ANDs and ORs and NOTs and bounded quantification. You can compose things and you still remain within the class. So in particular for NP, it's a very good question whether it's closed under negation, let alone whether it's probable closed under negation. So NP and classes in the polynomial time hierarchy are not really quite robust to get those kinds of results. But polynomial time, non-deterministic log space, non-trivially, and AC0 definitely are. And another caveat is that we really want those properties to be provable within the reasoning in the system. So, and here it is. It's a generic statement that if you can actually prove using reasoning with only concept from that class, that the class is closed under first order operations, then you get a system of arithmetic that precisely captures this complexity class, as in it proves totality exactly of the functions from this class. So this gives you an automatic way to take a logic characterization of a complexity class, whichever one your favorite complexity class is, and convert it into a theory of arithmetic. So I'm really out of time, but let me just say for AC0, it's direct. AC0 is closed under AC0. For polynomial time and for NL, it's a bit more work because you actually need to formalize Horn satisfiability and the proof that NL equal co-NL within NL reasoning, within polytime reasoning, but this can be done. An even trickier class, log CFL, SAC1, was done by Satoru Kuroda. And And basically the way you do it is you build the theory and then you generalize Bus-Witnessing theorem to the new setting. So just to say that not the only way of building theories. For example, Cook and Nguyen in their book, they also use an approach of taking a complete problem for a class and throwing it in as an axiom, defining axiom for that problem, and then building theories on that. But generally, at least you can definitely translate from descriptive complexity. Okay, so I'm out of time. So let me just say that this talk was mostly kind of a segue from this week's topic, finite model theory and descriptive complexity, to next week's topics, which will touch upon many different aspects of reasoning systems, in particular, I think, systems of arithmetic, from piano arithmetic to bounded arithmetics. But hopefully here you could see how you could go from the expressive power to a reasoning power essentially in one method. Okay, thank you so much. And any questions, comments?
Awesome. Thank you for a beautiful and enlightening talk, Antonina. Thank you very much. Questions, please. So I have some comments and questions. So in a different setting, I actually study theories over arithmetic and strings. And I'm surprised that there is this, I wasn't aware of this, these theories over strings and arithmetic that were defined by Cook and others. And I would be happy to chat with you offline about potential connections, because there are many open questions there, which have been open for maybe 70 years or something like that. And I wonder whether any of these connections can be helpful in resolving some of those questions. Some of them are complexity theoretic, others are more, decidability, and so on. But in any event, it would be interesting to, explore those connections. Any additional questions?
Yeah, I have one question.
Please,
about this SL equals L result.
Mm-hmm.
So the existence of expander graphs, you do it with the zigzag product. And that's what.
Yeah. Mm-hmm. There's a kind of a zigzag, yeah.
So which part is missing to get the formalization? Is it the log?
Yeah, what's missing is that you could prove the existence of expander graphs when you start with small things with constant expansion, and you combine them and you keep expansion constant. What to do when you start with something that does not have a constant expansion? That's what we haven't figured out.
Okay, thanks.
Hi, Antonina. Can you comment on these two approaches? You mentioned like Cook-Nguyen and your approach using finite model theory. So what are the differences between, let's say, the theories you get for NL by doing such things? Like, is there an easy way to, or are they exactly the same? They prove the same theorem. So what exactly happens?
They do prove the same theorems. I think Steve and Fong have in their book the connections, all the different ways, but I think, as far as I know, they do prove the same theorems.
I see, thanks.
So even the theory operating with Horn formula does prove the same theorems as PV, but interestingly, it's much easier to formalize the recursive definition using the Horn formula than go the other way around. Yeah.
Any additional questions?
So I'm trying to put together a question for Antonina. So I was struck by the same thing that Igor mentioned, that you were categorizing things that introduced all functions all at once versus things that sort of built up to get all functions. I've always categorized more the first order theories versus the second order theories. So we sort of have two different viewpoints of this. Does this mean there's really three different ways to set up bound arithmetic? Do you view it this way? I'm thinking of your paper with Steve on Crom and so forth, and with proving that NL equals co-NL. That's a different type of bootstrapping, you think, than the things that the theories use induction?
That's a different type of bootstrapping. Yes, but you would know much better than I do what are the different ways.
Well, I mean, I've certainly read all this. I just never. It's just you obviously have a bit different viewpoint of this. So I was interested to get your feeling about this.
Yeah. So you can definitely start with an axiom that gives you a totality of, for example, graph reachability or circuit evaluation problem, and build theory on top of that, and you end up with nice theory, universally axiomatized and everything. And I think you could prove the equivalence between this theory and the theory based on the descriptive complexity view, and the theories like PV that come from recursive definitions.
Right.
As far as I know, they're equivalent, but that's a very good way of saying that you need a different type of bootstrapping in each case.
Mm-hmm. Okay.
Yeah.
Good. I guess the other comment is seemingly we need to go to the second order versions of the theories to deal with these very weak classes like L and NL and so forth, and SAC1, I suppose, and so forth.
I guess just because we get AC1, since we don't have multiplication of the larger objects.
Right.
So, yeah. And going from descriptive complexity to second order is a bit more it's a bit easier than, at least for me, to think about, because in descriptive complexity, you do have those second order objects floating around.
Okay. All right. Thank you.
Thank you.
Thank you again, Antonina, for a wonderful talk. Thank you. So thanks to all the speakers for great talks. Thank you.
Yes, thank you to everybody. And I guess we will be on Gaza Town, at least some of us, after this.
Soon, yeah. All right. So see you tomorrow then. Bye-bye, everybody.
Or see you on Gaza Town, and I will
I'll
post
get it on.
in a second.
Okay.
Thank you so much.
Thank you. Fantastic talk. Thanks.